Thermodynamics Chapter 3. In this chapter, we begin to evaluate properties. We'll use the tables in the back of the book. We'll learn to sketch temperature, specific volume, pressure, specific volume, and pressure temperature diagrams for locating principal states on the diagrams. We get a lot of information from knowing what phase we're in and what to find. Use that to be able to find the properties at a particular state. We'll evaluate quality and properties of two-phase liquid-vapor mixtures, and we'll interpolate between two values, super important, and estimate the properties of liquids. We'll also apply the ideal gas model and polytropic process relations in this chapter. This chapter is really the basis for everything going forward and being able to figure out the values we're going to use, so it's really a super important chapter. We're, again, still just talking about closed systems, and a reminder from last chapter, the first law of thermodynamics is that energy is conserved, and we have our closed system energy balance equation, which is the change in energy, total change in energy equals the total change in kinetic energy plus the change in potential energy plus the change in internal energy, and that also equals the energy transferred by heat minus the energy transferred by work. We have talked a lot about phase in this chapter, and we'll learn how to read diagrams to know what phase we're in. And in general, the phase is whether it's solid, liquid, or vapor. That's really solid, liquid, or vapor is the phases we'll talk about here. It's possible for a system to have more than one phase. We could have a glass of ice water. That would be a liquid solid. So we can have liquid and solid. And we can have liquid vapor. We'll see that. That's our two-phase liquid vapor is another two-phase that we can have. Anyway, that's what we mean by phase. We have phase changes. Two phase changes coexist during changes in phase. We have these three different methods: vaporization, so vaporization, condensation, and melting, and sublimation. So when we have vaporization, we're going from liquid to vapor, and we have those two phases existing at the same time during vaporization. Condensation, we go from vapor to liquid, the reverse of each other. Melting is solid to liquid, and sublimation is solid to vapor. So pure substance is uniform and invariable in composition. It can be in more than one phase, but the chemical composition must be the same. So again, like a glass of ice water, that is a pure substance, H2O, but it has two phases at that time, ice and solid and liquid. We talk a lot about intensive properties in this section, in this chapter. We have temperature, pressure, specific volume, specific internal energy, and specific enthalpy. We'll talk a little more about enthalpy later, but enthalpy is the combination of internal energy plus the pressure multiplied by specific volume. And again, if you remember these specific values, so specific volume is volume divided by mass. Specific internal energy is internal energy divided by mass. And specific enthalpy is enthalpy divided by mass. And that makes those intensive properties. And those are tabulated in our book. And that's, we'll use the tables to find them. When we say that we're fixing the state, the intensive state of a closed system at equilibrium is its condition as described by the values of its intensive thermodynamic properties. Essentially, when we're fixing the state, we're looking up and finding all of the different properties at that state. In this class, we generally study a simple compressible system, which are pure substances, again, all one chemical composition, like H2O. or a uniform mixture of non-reacting gases. If the simple compressible system is in a single phase, given any two independent, so if we have a single phase, meaning that it's all liquid, all solid, all vapor, then giving any two independent intensive properties will fix the other intensive properties. So if you have temperature and pressure, you can find the other specific volume, internal energy, and enthalpy. And later we'll see entropy as well. But if you have to be in a single phase to only need two. And you can have any two of these listed intensive properties, and then you'll be able to find the rest. So if for a two-phase, if I'm in a two-phase liquid vapor mixture, pressure and temperature in that liquid vapor mixture are not independent. They're not independent, and so we need additional value. We use quality. X is the variable we use for quality, and quality is really just the ratio of the mass of the vapor present to the total mass of the mixture. We'll see some other formulas we can use to find that, but essentially we're just finding the ratio of where we are in the vapor dome, which we'll get to in just a minute, and it'll make more sense. But determining the intensive properties is fixing the state. So when we say fixing the state, we're really just determining the intensive properties of the system at that state. That's fixing the state. So for a pure, simple, compressible substance that expands on freezing, so these diagrams here are for expanding on freezing. Water expands on freezing. Most things don't. But this is what given these diagrams here show the pressure, specific volume, and temperature relation for something like water that expands on freezing. And we can see here that we have a three-dimensional diagram here. There's temperature, specific volume, and pressure. And so we can see our isothermal lines, our temperature lines going across, and anyway, that follow it. The top of this area here we call the dome, the vapor dome. So in this dome, we have a two-phase liquid vapor, two phases happening at the same time in this dome. The top point here is the critical point. This is the triple line. Anything on this side of this is vapor. On this side of the dome here, this is liquid. The critical point separates those two. And then down here at the bottom, we have a solid. So this area here is solid, and this would be a solid vapor, two-phase. And then in the middle here, we'd have a liquid, a vapor and a liquid. So taking that diagram and looking at it, we have a phase diagram here in B, and this is when we project this onto a two-plane, so of pressure and temperature, we have this this phase diagram, and we can see the same thing here, that this area would be solid, this area would be liquid, and this area would be vapor. The line itself is represents the two phases happening at the same time, vapor and liquid, vapor and solid and liquid. That would be where the two-phase happen. Over to the right here, we have specific volume and pressure diagram. And with each of these lines being isotherms, temperature lines, so these are all the same temperature. We have the critical point here where the critical point at the top of the dome, and then in the dome here we have a two-phase liquid vapor. Again, on this side of the critical point we have vapor. On this side of the critical point we have liquid, and then we have solid. I think I did blue. So they're saying this is solid here, and then we have solid vapor on the bottom, and so on. So that is our specific volume. This is a PV diagram. This is PV. This one is PT. And we'll see, we also do a temperature volume, a TV diagram, which we'll get to in a little bit. So more definitions. Oh, one more. Looking at it, this is for what other substances, and you can see it's similar. These contract on freezing, and but we have a similar. It's similar to what we saw in the other diagram that contract or that expands on freezing or water. But we have some definitions here that we'll go through, and then we'll see more of this. But the two-phase regions, so where two phases exist in equilibrium, it can be liquid vapor, solid liquid, solid vapor. In the vapor dome, so if we're in the dome, again, this is the dome, and if we're in this dome, then we're in the liquid vapor area of the chart. Two phases can coexist during changes of vaporization, melting, and sublimation within the two. We're missing one there, I think condensation. Within the two-phase region, pressure and temperature are not independent. The state cannot be fixed by temperature and pressure alone. We need another thing. We need to either find specific volume, specific internal energy, or specific enthalpy, and pressure or temperature. So when we're in this dome area, we need to have another variable besides temperature and pressure to be able to find our properties. The triple line or the triple point, this is where three phases exist in equilibrium. And the triple line is in three dimensions, and the triple point is a projection of the triple line onto 2 dimensions. So the triple point of water is used in reference to defining temperature scales. So we have the triple point of water being where it can be solid, liquid, and vapor all at the same time. Saturation state is the state at which a phase begins or ends. That's the saturated line. The lines bordering the vapor dome are the saturated vapor lines. So if I have the vapor dome, then these lines are the saturated line. So we have on this side liquid, we have on this side vapor, and this line on this side would be liquid, a saturated liquid, and on this side would be saturated vapor. The critical point separates those two. This is the critical point. In between, in the dome there, you'll have both liquid and vapor. So in here, this is two-phase liquid and vapor. But the line, that's the saturated state. So we'll see we have T-stat and P-sat. That's the saturated temperature and the saturated pressure. It's really the temperature at a saturated state and the pressure at a saturated state. The critical point is the top of the dome, and this is where saturated liquid and saturated vapor lines meet. The critical temperature of a pure substance is the maximum temperature at which liquid and vapor can coexist in equilibrium. The critical pressure is the pressure at the critical point, and the critical specific volume is the specific volume at the critical point. These values are found on the tables. They're listed in table A1, and the other tables actually give them to, it's sort of the last entry in the table gives you that critical point. Phase diagrams are projecting a three-dimensional PVT diagram, that three-dimensional diagram we saw in just a minute ago in the first one, onto a two-dimensional pressure temperature plane. The two-phase regions are reduced to lines. That's B above. And then saturated temperature and saturated pressure that are the temperature at which the phase change takes place at a given pressure. Saturated temperature is the temperature at which phase changes at a given pressure, and saturated pressure is the pressure at which a phase changes given a given temperature. And these are noted as PSAT and TSAT. And that would again be the saturation state lines, those values that were given there.